Hello guys, welcome back to another worked example video. So today's topic is going to be Lewis structures, hybridization, molecular geometry, determining polarity, and anything relating to do with topic 4. Sort of the difficult areas of topic 4. So I'm going to do 5 examples. The first 3 on this worksheet, and then I'll have 2 for the higher levels more specifically. But the first 3 are both for SL and HL. The only thing I'm going to add here is hybridization, which is technically an HL topic. So for the SLs, you don't pay attention to that bit, but I'll try and specify when I'm directing to the higher level specifically. I'm intending for this video to be for both types, both kinds of people, since there's not a lot of higher level content that is worth warranting a video on its own. So pause the video now if you want to try the first 3, and come back in a couple seconds. Alright, so I assume you're back now. So for the first one, which we have carbon tetrachloride, L4. So the first thing I want to do is add the sum of the valence electrons. So chlorine has 7, so we have 4 times 7 plus the 4 on carbon, which yields us 32 electrons. And so let's get to drawing. So C is our central atom since it's the least electronegative, and then we have Cl, 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 and then Cl. So that's 8 electrons, so 24. Yep, 24. And then if we do 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And that should be 24 electrons. So 0 electrons left. So that is the Lewis structure. And so let's go back to our so that's the Lewis structure. In terms of electron domains, well, we count so the things we counted for electron domains are, and keep in mind that we're measuring with respect to the central atom, so carbon. There are 4 electron domains since there are 4 single bonds. We count a single, double, or triple bond as 1 electron domain, and an electron lone pair as 1 domain. So this counts as so there are 4 electron domains. So the geometry of this molecule is tetrahedral, and the next step is to and now we have to determine if it's polar. One way we can so in order to determine polarity, I usually like to draw a geometry diagram. So we'll have a wedge. We'll have our wedge. And then we'll have our dash. And then here. Excuse me for my kind of derp my derp sort of electron geometry diagram. And then now we take the sum of each dipole. No, whoops. So there. So this is the least electronegative element. This goes to the more electronegative element. Likewise, and then likewise up here. And note here how there's no sort of easy flow across to form a net sort of dipole moment. What I could actually even do, I can go even further and add these vectors up. So we have that, and then something back there like that. And alright, so what if I dot plus minus, and then if I basically you can see here that I'm trying to add a vectors in such a way so that you can clearly see here that there's no vector sum, but um, what it'll amount to is that you can add these three bottom vectors here and you'll get a vector that's like that. And since those are equal magnitudes, since this would be, say we called this theta, this would be sine theta r, 3r sine theta, which is equal to that, and then that would be equal to 0. So since there's no net sum of the vectors, this would yield no polarity. Right? I don't know if that makes any sense. I probably doubt it doesn't make sense, but basically I tried to add up all the... So what I did was I first drew a Lewis structure just to sort of get a feel for it. Then I drew a geometry diagram based on the fact that, okay, there's 4 electron domains. And then I added the dipoles, these dipoles up here, to try and see if there was a vector sum that yields a net polarity. And there was no net polarity, so therefore it's not polar. So for the next one, OF2, first let's draw our Lewis structure. O F F. Oh, I forgot here. Whoops, I forgot to add up our electrons. So 7 times 2 is 14. So that would be 2 times 7 plus 6, which yields us 20 electrons. And I've already used 8, so 14, no, whoops, 12 even. 12. There's 12 electrons left. And if I dot those around here, that's 6. That's 12. There's 0 electrons left. Now, in order to help me determine polarity, so there's clearly 4 electron domains, but unlike the other one, this is a bent molecule, and now we have to determine polarity, which in order to do that, we should draw a geometry diagram. So our oxygen is in the center here, and then we have 2 fluorines. Oh, and I forgot. For the higher levels, that last one was sp3 hybridized. Since there was 4 electron domains, 4 minus 1 is 3, and that would yield to an sp3 hybridization according to the little formula to remember. You could draw out orbital diagrams, but I promise you that's not fun. So I forgot to mention it for the higher levels. The last one was sp3 hybridized. Now back to the regular content that I schedule. So what I'll do here is I'll draw our wedge dash to denote our lone pairs, and then F, F, and typically what is convention is you draw these little bubbles around lone pairs on a geometry diagram if there are lone pairs on the central atom. Oh, and I forgot, you don't draw those there. And now we look for our vector sum. So we, no, whoops, wrong way around. It should be that, and then we also have that. And if we add the vectors up, we get that plus that, and then this is our vector sum plus negative. So we can see here that since the vectors clearly add nicely to get us this nice net sum, therefore there is a dipole moment that goes something like this. Right? So therefore that molecule is polar, and for the higher levels, 4 domains again is sp3 hybridized. Lastly, for both standard and higher levels, for the third one, yields So the third one is BeCl2. Now, the first thing I want to note is that beryllium is actually an exception to the octet rule, so do note that. Regardless, we can still count our valence electrons, so there's 4 on beryllium, I think. Yeah, 4 plus 2 times 7, which yields us 18 valence electrons. And then if I draw our beryllium here, Cl, Cl. Okay, now that we've reduced it to 14, since each bond is 2, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and 1 and 2. So that should equal 0. And note that since beryllium is an exception to the octet rule, hang on, I think I made a mistake somewhere. Uh, four valence electron. No, there should be 2. Whoops. My bad. No, there's only 2. There's 4 electrons in beryllium, but there's only 2 valence. And so this should be 2. This should be, whoops. I did make a mistake there. Sorry, guys. Let's correct our mistake by deleting all that. So 2 plus 2 times 7, which is 16. Beryllium. Cl, Cl. And drawing those there is 12, and that gives us 0. And now we check to make sure everything obeys the octet rule. Both chlorines obey the octet rule, and beryllium is an exception of the octet rule, and it is happy with 4 electrons, so therefore that is good. Now we can, so it's pretty obvious here, there's only 2 electron domains, so this is linear. So we could draw a geometry diagram, and you know what? Let's do it. It's not going to look any different, much different, but for the sake of drawing it, we'll draw it out. So you can see here that we can, again, do the thing with the vector sum. So that's one dipole, that's the other dipole, and since these are of equal magnitudes, it's pretty obvious that this would yet net in 0. There would be a 0 net dipole moment in this molecule, because if you can imagine it's like playing tug of war, it's pretty clear to see here that since they're of the same length, there's not really nothing going to be happening. So this molecule is not polar. And for the higher levels, there's 2 electron domains, so 2 minus 1 is 1, so it is sp hybridized. Select all, delete, and then for the higher level, so that's all the standard levels stuff done. Now we can consider for the higher levels. Alright, for the higher levels, we will consider the first 2 here. No, the in class part should not be there. We will consider phosphorus pentachloride and selenium hexafluoride. We will not do the hybridization, since that's beyond the scope of this course. However, they are expanded octets, so therefore it'll be good practice. So pause the video if you want to try it yourself, and come back for the solution. Okay guys, welcome back. So we're going to do our so let's draw our Lewis structure. So the first thing I want to do is PCl5. First thing I will always like to do is add up our valence electrons. So phosphorus has 5, and then chlorine has 7, so 7. So then there's 5 atoms there, so 5 times 7, which yields us 40 electrons to use. And then I will draw our phosphorus, draw one bond between each chlorine, Cl, Cl, Cl. So that's that there, so each bond is there, and that was 10 electrons, so that would be 30 left over, and then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 4, 6. And then 2, 4, 6. So there we go. There is all of our electrons done. So that's the Lewis structure done. And we want to check to make sure that the outer atoms obey the octet rule, which they clearly do. 8, 8, 8, 8, 8. Yep. And now we check for no formal charge on the central atom. So if we count each electron as one, if we count each bond as one electron, we have 1, 2, 3, 4, 5. And on the periodic table, there's 5 electrons per phosphorus normally, so there's 0 formal charge. F, C, and then now we consider if it's polar. So to do that, we draw our geometry diagram. So we will have triangle Cl, 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 and chlorine is more electronegative, so we'll have that, we'll have that, and we'll have that, and then we'll have that, and we'll have that. From here, it's easy to see that these vertical forces will cancel each other out, and now we only have to consider the trigonal planar bit. And since these are of equal lengths, I can arrange these into an equilateral triangle. So let me denote that there, since those are of equal length. And then I can do that. And notice here that since all the tails to tip can add up to form a polygon, there is no net sum, so there is therefore no polarity. There's no polarity. Select all, delete. Last example here, selenium selenium tetrafluoride, so SeF4. So the number of valence electrons on selenium is, I think it's 6. Let me just check here on my calculator. There is a periodic table function, so let's check on there. So selenium is element 34. So there's 6 valence electrons in selenium, so 6 plus 4 times 7, which yields us, so 28 plus 6 is 34. And then, so let's draw out our, let's draw it out. So F, 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 F. So 34 subtract 8, which yields us 26. And if we first fill in our valence electrons on the outer atoms, so 2, 4, 6, 2, 4, 6. Alright, that should yield us 2, since there's 24 total and 6 each, and then we can just fit these 2 on the selenium atom. And check to make sure everything works out. So all the outer atoms have 8 electrons, so those obey the octet, and the central atom should have no formal charge, and as we discussed, there's 6 normally when it's neutral and not bonded to anything. And if we count each electron, if we count each bond as one electron, 2, 3, 4, 5, 6, 6 electrons, so no Fc. So that works out. Now we can determine our polarity of this molecule. So we can draw a geometry diagram. So E, and this is trigonal bipyramidal. No, it's square pyramidal. So we can we have to use 2 wedges and dashes. Oh, that was bad. That's bad. I don't like that. But we'll have our lone pair here, sort of doing that thing, and then if we this. Let's draw out our F, 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 F. It's pretty hard to, work with that. So, although this is a formal geometry diagram, let me draw something out that might actually make a bit more sense. So, I don't know if it's clear here, but you can sort of imagine a pyramid there. That's supposed to be pyramidal, and then we can add up our vector forces, our vector sum, which we can do it like so. And if I, here, for the sake of simplicity, we're going to just draw a plus there. If I do that, and if I do that, and if I do that, and if I do that. So adding these two vectors up, we can get something like that, and adding those two vectors up, we can get adding 1 and 2. Let's label them 3, 4, 1 plus 2, 3 plus 4. And since these are all the same, vectors, since it's the same bond, 1 and 2 equals 3 and 4, and since they're pointing in opposite directions, there's 0 vector sum, and therefore this molecule, wait a moment, no, it is polar, but we can see here that if we add these vectors up, 3 plus 4, we actually do get a small dipole moment, and therefore that's the dipole moment, and therefore that molecule is in fact polar. So yeah, therefore the molecule is polar, and yeah, thank you for watching. If you like this content, feel free to subscribe, all that fun stuff. See you later.